Yeah. Okay, so we're recording here. Today is the July 6th, and we're going to do relativistic linear momentum and relativistic energy. And what are we talking about? We are talking about what are you saying here? We're saying that every time we have new postulates like the one in special relativity, the consequences of these new laws will definitely yield some new, will definitely result in some new phenomena that were not predicted by the older postulates. In the case of the special relativity, this is a theory of motion. That's what special relativity is. Special relativity is a theory of motion. Which, by the way, must correlate to Newtonian theory at a certain limit. Okay? And this limit is the limit of lower speeds. So what do we mean? Newtonian theory breaks down at high speeds, and high speeds is comparable, is defined in terms of the speed of the light. So at a lower speed, special relativity must agree with Newtonian theory. In other words, Newtonian theory is an approximation of special relativity. Approximates to, I prefer, it's an approximation of special relativity. I prefer that. And the condition is this one here, for V much less than C. Okay, for V much less than C, then special relativity reduces to the Newtonian theory. But even more important, the equations of special relativity will be different from the equations of the equations of the Newtonian theory, but not that much different. Okay. The consequences may be different. The consequences of those new equations may be different. Not the consequences of these new formula, of these new equations, may be different. But equations will somewhat resemble that in Newtonian theory. Somewhat, okay? That's where we get to the case of, that's when we get to the case of the linear momentum, okay? Let's take a look how linear momentum is defined in Newtonian theory, right? Let's take a look. Here you go. Newtonian momentum is defined as being mass times velocity. So the role of the scientist here in this new theory of special relativity is to find out if this equation also will be applicable in special relativity. And I'm going to be even more specific, okay? I'm going to say V is going to be the V velocity of a point particle with respect to a referential A. That's how we should write the linear momentum of the particle. Let me do the demonstration, the illustration here. Right? So here you go. You are here in your referential A. You're observing this point particle P. And it's moving with respect to, doesn't matter what the velocity is. So the question is, what is going to be the linear momentum of this particle in special relativity? Okay, what is that going to be? If we apply the above relation in special relativity, if we investigate, right? If we investigate the above relation in special relativity, we find that linear momentum is not conserved. Don't forget that it is not conserved whenever remember the net force is zero, right? Oops, force is zero. Oh, which is a very important characteristic of linear momentum. Okay, so recall that linear momentum is conserved in Newtonian theory whenever the net force is zero. If we investigate the above relation special relativity, we find that this equation, this specific equation of linear momentum is not conserved whenever the net force is equal to zero. Because of that, if we want P to be conserved under this condition, right? Under this condition, net force is equal to zero. Then we must look for a different equation for P. What the equation that people find out that they know it works, and by the way, I'm going to put it as a vector right now. Ooh. Going on here. Oh, that's why. I'm going to put a vector here as well. So if you want the linear momentum to be conserved under this equation, under this condition, the net force equal to zero, then you must look for a different format, not a different equation, but a different format for P. The format that we find, that we do know it works in relativity, that makes the momentum to become conserved under net force equal to zero, is the following. I'm not going to prove that. You have to believe that. Relativistic. Yes, we are going to have m times va, m times v. Yeah, we do have this term, but then we will have to have a different term. And this other term is very similar to the gamma factor that I introduced before. But this gamma factor is not exactly the gamma factor for a very, important reason. It's not exactly the gamma factor because this V that you see right in here is the V of P with respect to A. Okay. Someone can argue, look, this is basically V, this is basically gamma if we take P as being a second referential, right? But it's very easy to remember. But it's not exactly because gamma is used only for a referential, for another referential. In this case, P is not the referential. P is just another particle that we're measuring the linear momentum with respect to referential A. And this particle can also have a different momentum with respect to another referential, a referential B, for instance, right? So here I'm going to write like that. Linear momentum of particle P with respect to referential A. And then we can also have the same equation for the linear momentum as taken from the referential B. Linear momentum of referential B would be linear momentum of particle P with respect to referential B would be given by this equation. Okay? But remember, this factor is not the gamma factor because the gamma is used only for transformations from one referential to another. Now, there is a very interesting interpretation for this term here. I'm going to copy that. There is a very interesting interpretation for the term and I want to warn you something about relativity. Like it or not, we still don't completely grasp relativity. Even professional scientists, they don't completely grasp relativity, even 100 years after it was formulated, okay? So the initial interpretation of this term here was that the relativistic mass. That was the initial interpretation of this term. Initially, the interpretation of this term would be in terms of the relativistic mass. And this relativistic mass has a rather interesting behavior. Okay, remember, this guy behaves like the gamma term, right? This term. And that its interpretation is like that. As the speed approaches the speed of the light, the relativistic mass increases, right? If the speed is half the speed of the light, we can do the math. we're going to get only 15% difference from the rest mass. What you have here is called the rest mass. This would be a 1 kilogram mass. You have put the kilogram here between parentheses, right? As the speed increases, okay, whoever the referential A is should be able to measure a larger mass for the particle. And as it approaches the speed of the light, this mass just goes to infinity. Okay, that was the initial interpretation that we had for this term that you saw. Nowadays, people are taking this interpretation with a grain of salt. Remember that I told you, right? Not everybody understands relativity deeply, even professional scientists. And the interpretation of the mass, of the relativistic mass, is one of the things that is still not very clear in relativity. And that was the initial interpretation of this term. Nowadays, they start saying, look, that's not exactly the relativistic mass. That's something else. What they're saying is that this term here is actually inherent to the momentum of the particle, and the mass of the particle is not necessarily increasing as the particle moves faster and faster. That's what they're starting saying right now. And because the mass increases, approaches infinity near the speed of the light, the argument would go like that, because you have a very large mass, it's going to be very difficult to apply energy to exceed the speed of the light for this mass. Okay, that's the interpretation that they used to give. But keep that in mind. So there are three schools of thoughts right now. One school of thought say that this term is a relativistic mass, that the mass does indeed increase. And then there's other school of thought. This term that you see here is unrelated to the mass of the particle and is just inherent to the linear momentum, okay? And that's what gets conserved in special relativity. This relative momentum, linear momentum, this relativistic linear momentum, we call the term above, we call the above term the relativistic linear momentum. But now we can start playing games with this relation. Now that we have concluded that we believe that this term gets conserved at relativistic speed, we can start using it to get other things, other important results. One of them is the relativistic energy. Recall from physics 37 recall the work kinetic energy definition from physics 37. Do you remember that? We use that in relativity as well. What is the work kinetic energy theorem? If you didn't memorize the work kinetic energy theorem, this is the time to memorize. It's a very important theorem. Okay, the work kinetic energy theorem relates the work done by a net force, right? Which is nothing but the integral of the net force. I'm not going to use the vectorial formulation. I'm going to use the scalar formulation, okay? from a given initial velocity to a final velocity, right? Remember that? Or in this case, it would be x naught to x because I am integrating in the s. But eventually, we put the v naught to v and integrate in terms of v. And what we get? We get that it is given by the difference in kinetic energy. Like that. Like that. Final kinetic energy minus initial kinetic energy. We can, we can apply this definition in relativity and figure out what happens at the end. Okay? And let's not forget that in Newtonian theory, the net force is going to be written in terms of the PDT, right? And that happens in relativity as well. That happens in relativity as well. By the way, we can go even a step further here. And I'm going to do the following. Here you go. I'm going to start putting S naught to S here, since I'm already doing this integration. I'm still going to put S naught to S. Okay. And now it's going to be only now that I'm going to interchange the dt here. I can put the dt divided by ds. Now that we're integrating in terms of dp is going to be the limits of the integration is going to be p naught to p, right? Here becomes v. And by the way, this v is going to be pa, velocity of a particle with respect to p. And eventually we manage to exchange this dp in terms of the velocity. It's possible to do that, especially in view of the fact that p itself is related to the velocity of the particle. Okay, right in here. Now eventually, I kind of I'm not going to do this step, okay? Just note, see. Just note, see, that dp is a function of vpa. Now we are going to apply the relativistic linear momentum here and see what happens. Einstein did that for us, and he got a very interesting result. Okay, it's a little bit lengthy, but it's going to be worth it. Okay, and by the way, if the initial linear momentum is zero, the initial kinetic energy is going to be zero as well. Okay, so I'm going to here write this equation here. What we're going to do here, let us calculate the net work required to accelerate a particle P from rest to a final velocity VPA. Final velocity VPA. So the way it goes is going to be, it's supposed to be something like that. If the initial velocity is zero, automatically the initial momentum has to be zero, right? So if the initial velocity is zero, this term here has to be zero. And this initial kinetic energy has to be zero as well. In this next step, what we're going to do, we're going to apply our definition of relativistic momentum. And the definition of relativistic momentum is right here. I'm doing that with respect to referential A. What we have here upstairs is called the rest mass. What we have here is what some people call the relativistic mass. Okay, and I don't need this term anymore. Don't forget, everything starts from the definition of work of the net force. This term here, because it's the rest mass, we can take it out. And by the way, we're not using the vectorial formulation. We are using the scalar formulation. That's a 1D case. 2D case is more difficult, of course, just like it's more difficult in the Newtonian theory. And we can take out the mass out of this differential. I'm going to place VPA right in here. And by the way, this integral is not that difficult to calculate, not just the integral, but also first the differential, right? We have to break down this differential in its components. Recall that what I told you before, right? Many of the equations in relativity doesn't require integration, but this one does. This derivation I'm doing here does require integration. What's important, but what is important, the important point to pass is that you do not need high-level calculus to understand some of the theory of relativity. Let's break down this term, which is going to reduce to what's going to be. Oh, apply the chain rule, right? Well, we make this term here constant first, right? And the next term is going to be what? Like that. Chain rule, right? And we're going to go for the next step. Right now, we have to solve this term right here. We gotta get the differential of this term. And this term is nothing but what? It's a power, right? And I'm going to emphasize that this is a power. But it's a power of half with a power of a negative value. Putting it in a different format so we can differentiate it more easily. In the next step, this term is going to become minus half, right? We repeat this term. We get minus half and subtract 1, right? And finally, we differentiate total derivative. Total derivative of this argument right here. Next step, we're almost there. It's going to be kind of big, right? The total derivative of 1 is going to be 0. So we are left with the total derivative of this term here. And now we can start thinking in terms of thinking about simplifications, right? This negative sign that you see here can go outside. When you subtract 1 from half, you get minus 3/2. Now I'm going to get rid of some of the parentheses. And by the way, this negative sign here is going to combine with this other negative sign here, which will result in a positive sign. The c squared that you have here can be taken out of from inside the differential. Symbol. And we are left with, here we go. Now we are ready to write everything the way it's supposed to be written. We have to write 2 because we're differentiating the total derivative, right? We're differentiating VP squared, VPA squared, and then we end up with an integrating term that is just the same as this one. Let's see if we can simplify that further. Hopefully we can. The first simplification that we can do, an obvious one, is collection, is the factorization of DVPA. That's the first one. The next one we can do is this 2 here. Cancel out this 2. And then we can combine VPA with VPA, right? To get the square value. And by the way, there is one more thing that we can do. This term here that we have is kind of similar to this term here. I'm going to do in the next line. This term here is nothing but what? I'm going to get 1 divided by that. Okay. And then we have to change the sign of the 3/2. We're not quite there yet, but we're getting close. I have someone knocking here at the door. Let me pause momentarily here. Thank you, thank you. Okay, so this term here is nothing but the square root, right, times the first power. That's what it is. That's what Einstein must have found, right, when he was doing his derivations, and he was surprised that it was rather easy to integrate all those terms. And we're gonna go the next step. And the next step is going to be this term here, taking out of the parentheses, right? We do not need this term anymore. We're not quite done yet. We're not quite done yet. Okay, we have to put everything under the same denominator. And when we put everything under the same denominator, we are going to get this term plus this term. See that? I'm going to take out of the parentheses here. We don't need the parentheses anymore. And look what a nice simplification we are going to get. The VPA term cancels out. The VPA term cancels out. Deixa aí na mesa. Daqui a pouco eu vou.
Você não tem mochila de costa, não, né?
Okay, see. That's my brother-in-law. Here you go. Let me cancel this one here. Right? And what else we do here? We combine finally, right? Let's combine. It's going to be, I'm going to put a parenthesis here. Combine this term with this term. We are back to the 3/2. We're back to 3/2 here. We got rid of the 3/2 first, right? And then we came back to the 3/2. Amazing, right? That's what that whole method is all about. It's something rather simple. Let's not, don't forget that it's not the momentum yet. It's just the, let's see, let's go going back here, right in here. Like that. Is this term right in here. What we derive with this term. And we can replace it with this one. There you go. I didn't take out the mass from the integral yet, but I will be able to do that. Let's see if we can finish it. One more student. We're gonna go in our break very soon. I'm gonna put my kinetic energy here on this side. Okay. One more student. Go. I'm gonna simplify this guy, but I can take it out my mass. That's the rest mass. And I'm gonna do even better, shrink a little bit more this integral, like that. And now that we are integrating V, we can change our limits, right? we can change our limits. Now that we have the VPA here, we can put that PA like that. VPA. Like that. And then, what else can we do? This integral is not difficult, right? This integral is not difficult at all. We have a VPA term here. We have a VPA squared term here. We have to worry just about constants, right? And I'm gonna come up with the final result, and then we're gonna get our break. But of course, before we have to take attendance, the final result is going to be something like that. I'm not gonna do the details. And then we are going to work out the consequences of this formula. And by the way, this is not half, it's minus half, right? Minus half, when we subtract one, becomes minus 3/2. The c squared that you see comes from this term. The negative term that you have here is going to cancel out this negative term, so I don't have to worry about that. And we have to put the limits of my integration. The limits of my integral. Integral. Oops, right in here. I'm gonna put 0 and then final velocity of the particle with respect to differential. Interesting. Differential A. What's going on here? Something odd happened that I don't quite understand. Okay, so it's ruining my masterpiece because that's 0. Good. Now let's see if I can get that. Yep. And now I can finish it. Good. Not quite there yet. Imagine how many times this. Oh, I can cancel, right? I want to cancel the 2. So we end up just with c squared. Apply the limits. Well, when we apply the limits, this term remains whatever it is, but we have this 1 minus 1, right? That corresponds to VPA equal to 0. What else can we do? Okay, one more step before we finish it. I'm going to get this term moved inside. Right? And this term here moved inside. And then I'm going to put it in the format that most of you will recognize. Einstein's famous equation, right? MC squared. So we have an MC squared term here in this equation. And I'm going to put I'm going to put a square root here. Okay. See the MC squared term here? MC squared term here. That's what the kinetic energy is looks like in relativity. This term here is a rest kinetic energy whenever the velocity is equal to 0. Not the kinetic energy, sorry. This term here is a energy of the particle whenever its velocity is equal to 0. Okay, rest energy of the particle. And here is a term that is due to the is an energy that whenever the particle is moving. Okay, we are going to work out this equation in more detail and its consequences. Okay, so for now, let's take attendance. That's attendance. Okay, today is the 6th. Sydney, are you there? Good, thank you. Next is Amy. Are you there, Amy? Amy is not here. Next, Andy. Are you there, Andy? Yes. Next, Alex Hernandez. I can see Alex in there. Hi, Alex. I'm gonna put a star on Alex's name. Oh, here you go. Thank you, Alex. Sartak. Thank you, Sartak. Basilio Lopez. Basilio is here, right, Basilio? Thank you. Joshua Mohan.
I'm here.
Thank you. Zaid Nava. I don't see Zaid. Sumana. Thank you, Sumana. Alisa. Hello, Alisa. Thank you. One more. Karsika. Karsika. I don't see Karsika here. Mary. Hi, Mary. Raymond.
I'm here as well, Professor.
Thank you. Ashley Tai.
Here.
Thank you. Kyriakos. I don't see Kyriakos here. Nope. And Alexis Valley.
Here.
Thank you. Alexis Valley. Good. And how many students we have? 12. Yep. We have 12 here. Good. So any questions before we go to our break? It's almost 9:05 now. Break. 9:05 a.m. to 9:20 a.m. And I see you in, there's no questions. I see you in 15 minutes. Back. Okay, so what else can we do is that? Okay. Let's check. Like, remember that I said under certain conditions, circumstances, relativity must reduce to Newtonian theory. And the condition, the circumstance, right? Under certain conditions instead of circumstances, right? The condition, this condition is B much less than C. And what we're going to do? And we have V divided by C right in here. So what we're going to do, and don't forget, it should be V PA, right? Instead of V, we're going to put V over PA. what we're going to do, we're going to apply the binomial expansion, binomial approximation, which is nothing more than a Taylor series, which is nothing but the second term of the Taylor series, which is nothing but the second term expansion of the square root you see above, or okay, so we go. I'm gonna do like that. This term is in reality minus half, right? Minus. Oh, he didn't do it. Huh. Let's try again. Okay, now we did it. Why it didn't work before? Minus half. Here we have our x squared, by the way. How does the binomial approximation works? Is going to be, oh, it's very important that you memorize the binomial approximation because we use it almost all the time. Is the first term plus the power, okay, whatever the power is. In this case, the power is half. Multiply it by this term here. That was the binomial approximation with, I'm gonna put a parenthesis here. There are more terms, but the binomial approximation, the name binomial approximation means that we get only up to the second term of the Taylor expansion of this formula. And we can simplify it. Right now is not an approximation, but just a equality. The negative term cancels out with the negative term. The 2 goes downstairs. Okay, and we have this relation, this approximation, which we are going to apply to the kinetic energy that we just derived. Now I'm gonna use this term. I'm going to put MC square in evidence. I'm gonna make an equality first. And then we have the -1. That's gonna be equality for now. Now I'm going to deal with the approximation. Here you go. And then what's going to happen? The 1 is going to cancel out with the 1. One cancel out with the 1. This term here becomes on its own, and that shouldn't be an approximation here. That's an equality. The approximation is here, right? And then look what they're gonna get. In the limit, when the velocity of the particle is much less than the velocity of the light, hey, c squared cancel out with c squared. mc squared has always been in the formula of the kinetic energy, has always been. It just happened that the c from the mc squared cancels out, okay? We can say that. That famous formula of Albert Einstein has always been in the term of the kinetic energy. It just happens that the c squared that's upstairs cancels out with the c squared downstairs. Let's see, someone has a message I need to do, okay? So that's the nice result that we can get from relativity. Now, what else? Going back to what we had before, that's the exact equation for the kinetic energy. I'm going to keep on elaborating on this equation. Let us continue elaborating on the equation, on the result for the kinetic energy. Right? Here you go. Consider that there is no potential energy. Assuming that there is no potential energy, assuming that there is no potential energy, we're dealing just with a free particle. We are just dealing with a free particle. No gravitational force, okay? Force around. We can here write the above result in a different way. What is negative here will become positive on the other side of the equation. Okay. And now, what we end up having here, we can call the total energy of the system is energy due to motion, and it is an energy due to rest. Okay. What you see on the left side of the equation is the sum of the energy due to motion, the kinetic energy, and the energy due to rest, mc squared. Okay. Again, we are assuming that there is no potential energy, okay? If there is a potential energy, of course, there will be an additional term here that we have to sum up. But by the way, what this term here is can also be assume that there is no potential energy. Assume that there is no additional forces, right? Applied to the particle. And we're just dealing with a free particle, no gravitational force around, no other force around, which would result in there are no additional forces. If we introduce a gravitational force there, then we would need to have a potential energy term. So what you see on the left side of the equation is the sum of energy due to motion and energy due to rest mass. And by the way, we can interpret the second term as some sort of potential energy. Okay? Let's say rest potential energy. Sort of rest potential energy. That would be a nice interpretation. So it would be the potential energy due to the atoms of the mass that are connecting each other. And here, Einstein's famous equation. Energy of rest, denoted by E naught. And there are other consequences. So when scientists start looking at this formula here, they start thinking, can we possibly extract energy from, let's say, a 1 kilogram mass? And if we can do that, how to do that? Can we possibly extract energy from a 2 kilogram mass? Let's take a look. What the 1 kilogram mass, what's the rest energy of 1 kilogram mass? Then we compare with energies out there. It has to be a very large number. It has to be a very large number because we are multiplying the mass with a very large number, c squared. 300,000 kilometers per second, 300 million meters per second. You square that, and then you get an even larger number, right? Let's just have an idea of the order of magnitude of the energy that we are talking about. Okay, order of magnitude of the energy of a 1 kilogram mass at rest. Right? Should be 1 kilogram, 300. I'm going to put this number elsewhere. I'm going to put this number right in here. Okay, 300,000 million. That's the type of energy we're talking about. Format. And let's see what we can do with this type of energy. Scientific. It's best put in scientific format, right? This number is so big that it's best put in scientific format. And by the way, that's joules. That's joules. So C, I'm going to put C here. I'm going to put rest energy of a kilogram mass. Subscript, yeah. And by the way, let's write that down between parentheses. Joules, right? Yeah, joules. But I want to express this term not in joules. What about expressing this term in kilowatt hour? Kilowatt hour is just how energies at home are used, are measured. A household spend roughly, in the low side, right? In the low side, 300 kilowatt hour per month. A household. A small family, let's say 2 people. The person that the family that rents my house downstairs, for instance, they spend on the average 320 kilowatt hour. Is a couple, right? And 2 kids. That's what they do. but they don't use air conditioning much, right? Here in the United States, the story is different. We use lots of air conditioning in the state, and my average expense, because I use lots of air conditioning, right, during the summer, would I spend like 600 kilowatt hour during the summer, and here the summer in Brazil is very hot. So I would say my average expense would be around 450 kilowatt hour during the year per month. So let's see what this much energy is in kilowatt hour, okay? So we can have an idea. I'm gonna prepare the equations. We have to transform joules into kilowatt hour. And let's see how it translates. Okay. For 1 kilogram mass, for a fine. Here you go. Example. Let's put that example. Determine the rest energy of a 1 kilogram mass in units of kilowatt hour. That's how the electric company measures our consumption at home in units of kilowatt hour, right? I already have the number. I calculate the number for you in joules, but I calculate the number in joules. But we need to have a better idea of what this is in kilowatt hour, 10 to the 16, right? Applying Newton's, applying Einstein's relation, right? That's 9.0. I don't like this X. I prefer this other one. Here you go. 10 to the 16 joules. Yeah. And now we are going to convert kilowatt hour into joules to see what it represents. 1 kilowatt hour is what? Is 1,000 joules per second. That's what 1 kilowatt is, 1,000 joules per second. But then multiplied by hours is 3,600 seconds. Okay? And here you go. 3,603.6 times 10 to the 6 times 10 to the 6 joules. Second cancel out with second. That's what 1 kilowatt hour is. 3.6 times 10 to the 6 joules. And now we can convert joules in kilowatt hour. Consequently, 1 joule is like that. And like here, 10 to minus 6. Kilowatt hour is a lot in terms of joules, right? 1 kilowatt hour is a lot. So let's convert that in kilowatt hour. 10 to minus 6 divided by 3.6. 10 to minus 6 divided by 3.6. Going back here. Ten to minus 6 divided by 3.6. And look what I'm getting here. I'm still getting a large number in kilowatt hours. 2.5 times 10 to the 10th kilowatt hour. Okay, we are dividing by a large number, right? We are dividing by 10 to minus 6, but this number is even larger. This number is even larger. How many households does it represent on the average, right? Households. How many houses can you power per month with this energy? Let's say the average household spends 450 kilowatt hour per month. Wow, it's 55 million houses. That's what 1 kilogram mass, that's the type of energy that 1 kilogram mass has. The rest mass of a 1 kilogram. We're talking about feeding, we're talking about powering 55 million houses in a single month. Let's say each house has an average of 4 persons, right? 4 people. So we're talking about how many people? We're talking about well, let's say, man, 222 million people per month, providing energy for 222 million people, right? We can even divide that by 10 to the 6. 1, 2, 3, 4, 5, 6. And then that's the population of the United, no, that's the population of Brazil. United States more 300 millions. So you can power a whole country, a large country, for 1 month with just 1 kilogram, only if you could figure out how to extract energy from, let's say, 1 kilogram mass of water. That's not an easy task, right? But people have been able to do that with atomic bombs, for instance. They have been able to extract this energy, but it's not a substance called water, it's something else. It's plutonium, it's uranium. From the practical point of view, it's easier to extract energy from those substances, from those atoms. Maybe one day we'll figure out how to extract energy from regular masses out there. Million people, millions. So when Einstein derived this equation, and scientists saw how much energy can be harvested from a mass, they start thinking, hey folks, how can we take advantage of this huge amount of energy? Okay, so here you go, for a 1 kilogram mass, so 1 kilogram mass can generate, let's see, the above energy correspond to, here you go, the above energy corresponds to how many kilowatts? Correspond to, man, 2.5, 25 trillion kilowatt hour. 1,000, a million, a trillion. 25 trillion kilowatt hour. It's like corresponds to, we go, nine times 10 to 16 joules correspond to 25 times 1,000, no, it's a billion, not a trillion, right? 1,000, a million, a trillion, 25 trillion billion kilowatt hour. The average household spends on the order of 450 kilowatt hour. Okay. Here you go, 450 kilowatt hour per month, spent per month. Per month. This corresponds to 55 million households, houses. 55.6 million houses. 55.6 million houses. For an average of 4 people per house, this corresponds this corresponds to a monthly amount of energy enough to power 220 million people. That's what we call back of the envelope calculation. 222 million people, right? Is the population of Brazil, population of Nigeria. Let's take a look. Which country? In 1 month, you can power a single country with 1 kilogram mass, with the energy contained in 1 kilogram mass. Population. Largest populated country, right? Largest populated countries. Okay, that's the world population, 8 billion. China alone is 1 billion, almost 1.5 billion. India is getting there. It's going to overpass China. United States is 335 million. You know. Indonesia, yeah, highly populated country. I remember the time that Indonesia didn't have that many people. Pakistan. Oh, Nigeria already surpassed Brazil. Just recently, Brazil had more population, has more people than Nigeria. Okay, just recently. So we are talking about 1 kilogram mass the energy in 1 kilogram mass can power one of those countries for a whole month. For a whole month. That's how large the energy is of. It is. I remember just last year I checked Nigeria. Nigeria had less people than Brazil. Huh. But that's because the rate of growth in Nigeria is very large, something like 5% a year. Brazil is growth rate of Brazil in the population is similar to that of the United States. So Nigeria passed Brazil. Mexico, yeah, Mexico is a large country as well. Lots of people in Mexico and Russia, Bangladesh. Okay, and that's just for you to have an idea of the amount of energy that just a 1 kilogram mass can provide. The rest energy of 1 kilogram mass. Let's go back, let's say 9:53. Huh? Our last break ended at 9:20, so we still have time. Yeah, 9:20. Let's go another 20 minutes. Do you have any questions so far? So that's the type of thing that scientists do, okay, whenever they're discovering some new stuff. Eventually, scientists figure out that the way to tap the energy, this huge amount of energy, was by first nuclear fission, and then by nuclear fusion. You cannot get any type of substance. You cannot get any type of material. You have to have a specific type of material and specific conditions to generate this type of energy. And don't forget, you still have to make sure that whatever energy you are inputting to is less than the energy that you are getting out. Okay? You still have to make sure that. You have to make that sure. It's not that, it doesn't make any sense for you to spend 50 billion kilowatt hour to generate 25 billion. It doesn't make any sense to do that, okay? Because you'll be spending more energy to create less. You'll be wasting energy. It's just like, spending $1 million to get something that costs only $100,000, right? It doesn't go this way. And eventually, scientists figure out that they could do that with either with plutonium or uranium by using nuclear energy. And what are the other consequences? Okay, let's continue working with our result that you have right in here. That's the energy of the net energy, right? The total energy is not the rest energy, not just that the rest energy, is the rest energy plus the moving energy, the kinetic energy, right? I'm gonna emphasize that. Kinetic energy plus rest energy. Like that, rest energy. It's all implicit right here. It's not difficult to remember, right? If you remember MC squared, then you can easily recall the fact that we are going to have a square root downstairs here, which is similar to our gamma factor. So if you memorize the gamma factor, it's not going to be difficult to recall that. And by the way, gamma is 1 divided by that, right? So what else can we do? Well, we can do something else. We can investigate what happens if we multiply the velocity of the particle with the energy. We can do that. And this type of things you figure out only after you have worked several hours with those equations, right? It's not that the way we're teaching here in the classroom. Is this thing going to be important or not, right? We do not know if it's going to be important. It's energy times meter per second, joules times meter per second. Well, what's that, right? Well, there is there's an important quantity that you're going to see that's going to be related to this formula that you see. And I'm going to make it simpler for you to figure that out just by ensuring that the term is bold-faced. Do you know what this quantity is? Right? Do you know what this quantity is? Let's go back to our notes here. I don't even want to type it. I'm just going to copy and paste it. Recall that I don't want to use okay, we can use that. We can use vectors, no problem. Well, I'm not going to use vectors. Let's take out the vectorial symbol here. Let's just deal with the scalar. That's what we have right in here. Right? Energy times speed is related to the relativistic linear momentum. That what we have discovered as we investigate further and further the consequences of that equation, PC squared. We remember that we covered that in physics 38. Physics 38, we were able to find out what was the linear momentum of the photon. And that was the equation. That was the equation that we used. Okay? So there is a relationship between energy, total energy, and the linear momentum in relativity. Okay. What else can we do? Some little magic, right, that we can do. VPA, okay, I am going to do the following. Don't see that we have a single P here. What if we multiply P on both sides of this equation, right? I'm gonna multiply P here and P here. And then we get P squared on the right side. Okay. If we get E squared, going back to my equation for E, here you go. If we square my E, we get something else like that. Oh, interesting. Yeah, we get something else like that. Why are we doing that? There's a reason why I'm doing that. Just recall, we go P squared times C squared. I'm gonna have my P squared here. That's my P squared, and that's my C squared, right? What else do we get? Like that, and then something like that. I'm squaring whatever is inside the parentheses. Okay. And then I'm going to do something else. That's the relation we have. I'm gonna add the term of the rest mass. Let's not forget that P squared times C squared, P squared times C squared has units of what? Has units of energy, momentum, and V. Okay. And what we do next, we're going to sum this term to the square of the rest mass. And let's see what we get. Left and right. Ideally, right, we should be just putting this term here separately. So we have a explicit relation. What else can I do that? Okay, m and mc squared, right, can be taken out. But I'm going to only c square. Only c square here. C square and c square. And then at this point in time, you should already be guessing that when we combine those two terms, we're going to have some sort of simplification, just like we did before. So at this point in time, you should start to have a feeling, right, that those equations may yield to some simplification. And that's what I'm gonna get those two terms under the same denominator. Okay. Do you see what's happening here? This term here is going to cancel out this other term here. And let's see what this is gonna take us. This term here cancels out with this term here. And c square is going to combine with c square. Let me do an additional step here so we don't get lost, right? Here you go. Yeah, let's do this additional step here. Is a negative sign here. C square cancel out with c square. C square cancel out with c square. And now you can see more clearly that this term cancel out with this term. We do not need the parentheses, but we are going to need this one now. M squared c to the fourth power. Okay. Did we have something like that before? Here. That's what E squared is all about. Okay. So recall that. Recall that. And we finally have a different relation that's very useful. The square of the energy, of the total energy, is equal to the square of the rest mass plus the square of the moving, of the kinetic energy. Let's see, the square of the energy associated with motion. Here's the A energy associated with motion. Here's the energy associated with motion because we have the P in there. Very important relation. And we can even represent this relation as a right angle triangle, right? P is one side, MC squared is another side, and E is the hypotenuse. There's more. What if, no? What if mass is equal to 0? Like in the case of the photon, like in the case of electromagnetic radiation, EM radiation, or the photon, the particle, the photon. Now we can have this relation, right? Mass of the photon is 0. And that's the relationship that we get between momentum and energy. PC equal to E, or E equal to PC. So the momentum is going to have a linear momentum. The photon is going to have the linear momentum that's going to be given by its energy divided by C. So those are the interesting results that we have in relativity. Also, do not forget, if the particle is at rest, P is equal to 0, right? Special cases where and the energy is that famous Einstein equation, 1011 mc squared mc squared. It all comes from here. I think, let's see, 1010 now. Let's take a look at the book, right? What we have in the book. So you can have an idea that we're covering everything. Login. While launch. Now, let's take a look at relativity. Electric potential, 30, relativity right in here. Simultaneity and time dilation. Okay, we saw that in the video, right? But once you have time dilation, you can have that problem in simultaneity. Whatever events are simultaneous in one referential, it will not be simultaneous in the other referential, which was exactly what you saw there in that video of the mechanical universe, right? The relativity of length is the length contraction. Lorentz transformation, we did them. Relativity of velocity, which is derived from the Lorentz transformation. We did the Doppler effect, the relativistic Doppler effect, and we did momentum and energy. So we are done with this chapter. 37.1 all the way down to 37.6. Done with 37.1 through 37.6. Let's see what the cumulative material is. And that's for the final exam. We're going to copy and paste what we did before. back. Let's see, light as a wave. This one is going to be exam 3, right? I didn't write it down. Exam 3. Exam 3. And lab 1. I'm going, and then I combine everything. That I have written down. Let's see, not this one. Material for exam 3, yeah, we have it here. Exam 3, yes. Exam 3, everything is repeated here, right? So let's make sure 35. I just want to, I spell out what the material is, right? So I don't need that here. The students coming. Okay, I can take it out. Exam 3. Exam 3. I wrote down exam 3 everywhere. Lots of things that you can see, right? And that's exam, okay. That's exam 2 and exam 3. 37 we left for the final. And then we gotta look for exam 1. Exam 1 right here. Exam 1, 2, and 3. Go all the way down. Every chapter we have covered. Okay, go. 36, and then we covered 37. Chapter 37. We still have chapter 17. Don't forget, we went back to chapter 17, right, to cover 17.6, to cover the Doppler effect, so you can have a connection between, it's not, yeah, that's the one, 17.7 and 17.8, so you can have a connection between sections, right? Sections, here's sections 2. All the way down to 6. All the way down to 6, yeah. 1, 2, okay, and let's not forget that we still have labs 2 through, that's gonna be, what, 7? We still didn't do lab 7. The final is gonna include everything and everything else that we're gonna cover. For the final exam. For the final exam. Chapters, all sections of chapters, sections. Exam 3, it's better, okay? And then, nope, take out. I want to emphasize this one is exam 3, right? So I'm gonna put boldface. And plus whatever we cover, plus whatever we cover until whatever we cover next week. Okay, next week is matter waves and the atom. Any questions? Let's see, how long is the final going to be? It's going to be 2 hours. The final is going to be 2 hours long, 8 o'clock to 10 o'clock. That's right. The final is testing lots of contents. You're right. The final, don't forget that we're going to have these chapters here are going to have a larger weight. Okay. Let's see. Oh, this material here. Yeah, this material here is going to have a larger, oh man, even more. This material here is going to have a larger weight, anywhere between 30 to 60%. Whatever was not covered in the partial exam. So what I suggest you to do is to concentrate on this part of the material, and everything else should come more easily once you review them. That's something that we learned. Once you learn something in life and forget it, okay, later on it's much easier to recall it back. Be the same, yeah, that's right. Multiple choice, fill in the blanks, that's right, and numerical questions, that's right. Yeah, it's gonna be the same format as the partial exams. Same format as the partial exams. How are the lab tested? Are the lab, oh, it's gonna be questions from the lab, right? Whatever activity that you did in the lab, I'm gonna extract some information from whatever we did in the lab, and I'm gonna put a question there in the lab. For instance, R squared, right? Find the CL, find the confidence level. At this point in time, you should be able to know how to use, for instance, right? How to use the table that I provided you. And then you should know what was done in the lab as well. The graphs that you plot, how you plotted the graphs, which were the regression equations for some of the plots, things like that. Not much difficult. Now, if you work it in the lab report, you should remember that. And this fraction, oh, I meant 2037 here, right? Yeah, a typo. Let's go back to the note. Any more questions? Notes here. 36 is diffraction, 37 is relativity. Okay, so let's relativity. So we can locate ourselves better. Here is going to be Doppler effect. Right? Here is diffraction. Diffraction. Yeah, diffraction. That's right. 35 is what? 35 is interference. Wave out. Don't forget, that's wave optics, right? Here is wave optics. Interference and diffraction. Here are the sections of electromagnetic wave and geometrical optics. Here, gotta write that down too, sections 15, 16, right? Gotta look at the oscillations, right? We had oscillations. Let's write it down so you can know exactly what each chapter is. Oscillations, waves, oscillations, waves 1 and waves 1. Here is waves 2, waves 2, and waves 2 means, and what about 33? Wave 2 is like sound related material, right? Which includes Doppler effect, but Doppler effect shows up only at the end of the of the course. 30, let's see, electromagnetic oscillation, electromagnetic wave. 33 is electromagnetic waves. Yeah, we have it. Oh, this is electromagnetic waves too, but just part of electromagnetic waves. Magnetic waves. Someone is trying to come in. Yeah. And if you recall, right, in electromagnetic waves, let's take a quick look. It's a funny thing that sometimes in physics, we use something that was not derived, right? And now, radiation pressure. Let's see if we can go there. Intensity, it should have been here or here. Let's see that Einstein equation. Yeah. Okay, so that's what we covered in the first round of chapter 33, right? Any more questions? So we have another hour and a half before the exam. And so many students we have here. We have 13. Did anybody arrive later? Let's see. Going here to the attendance. Is everybody here? Kyriakos. Kyriakos. Aini, are you Aini there? I don't see Aini there. Okay, 13. There are 13 students, but I have only 12 here. Let's see what's missing here. Karsika, are you there, Karsika? Yeah. Just say you're there, Karsika, so I can put attendance. I can write down your attendance here for you. I'm gonna give Karsika a star here for now. And let's go for our break. Okay. So break or from, let's see, 10:30 a.m. to 10:45 a.m. What do you think? I'm thinking here. What about I'll give you this hour and a half so you can prepare for the exam, review everything. Okay, let's have an hour and a half break so you can use this time for studying for the exam. We're just one chapter behind. I don't think one class behind. I don't think it's a problem. We can easily catch up in the next few days. Okay, let's do that. So break from 10:30 to 11:59. Okay, let's do it this way. Any questions? I will see you in 1 hour and a half. That is